All right, let's go ahead and get things kicked off here. So I want to thank you so much for attending today's session on extending Python with the power and safety of Rust. Rust is a super cool language that can be used for a whole lot of different things. People often refer to it as a system programming language similar to C++ and C, and that is definitely true. But you can see Rust kind of popping up everywhere, not just for doing system level development, but for doing web development, building, REST APIs and stuff like that in the cloud, using it for task automation, things like that. But one of the other powerful uses of Rust is the ability to use it to write Python extensions. Python is a super popular language, especially in the data science and machine learning and AI world. It's very easy to work with, but Python suffers from being slow. So typically when you're using Python with things like NumPy and Pandas, those libraries are not really written in Python. They're written in C or C++. Well, sometimes the code that you need to write needs to be faster, and there's not an existing C or C++ Python package out there for it, or Python extension. And so you, with a little bit of Rust knowledge, can go off and build your own Python extensions and then in Rust, and then connect them into your Python program. And that's going to be the focus on what we're going to do here in the next hour or two, is take a look at how you would do that. What are the tools and stuff that you use? And then we'll take a look at what it looks like when that code executes. We'll even explore some of the performance gains that you can get from that. Okay, so with that said, let's go over a little bit of introductory stuff here, and then we'll get straight away into the coding. So first of all, a little bit about us, Training for Programmers. Up to this point, we have been delivering basically free training classes in a number of different formats. We've done all-day classes, we've done shorter webinars, we've done extended webinars, kind of like today, setting aside 2 hours instead of 1. But the goal here is to deliver the same high quality training that you would encounter in a corporate training environment. So when I'm not teaching these free classes, I'm teaching private classes for large companies. So the goal here is to bring some of the things we do in those classes and bring them to people for free, or if we ever start actually selling courses, offering them at an affordable price, so that basically anybody in the world can take these classes. We deliver the training online through Microsoft Teams. It used to be Zoom. But the idea is that anybody anywhere in the world should be able to take this training if they have a web browser and an internet connection. Not just in the sense that they can attend, like they can watch the training itself, but we do all of the coding using GitHub code spaces. So when we get over to the content part, if you have a GitHub account and you haven't used up your free allotment of code space hours from GitHub, you can actually code along with us and actually run the code and everything else. So our goal here is to make this an incredibly useful and practical training for anybody in the world. Right now, we've been focusing our training sessions in on Rust, but I actually teach a lot of different things: Rust, .NET, JavaScript, Python, a whole bunch of different libraries and frameworks surrounding those technologies, and a whole host of other things. And so we're trying to focus in on things that are popular and upcoming so that people can take these skills and use them to get a great job or to continue to enhance the career they already have. We also want to empower people to be able to work or to work where they live. So many times people have to up and move to another location in order to find a job. Sometimes that's across the state or across the country, or sometimes that means internationally moving. With the power of the internet, people should be able to stay where they want to be, stay where their families and local communities are, and yet still be able to do their programming and build their career. So our goal here is to empower people to stay where they are, or at least where they want to be, and have a great career. We also, in some of our classes, make use of AI tools to enrich the human experience of programming computers. In this particular session, I won't be talking too much about AI coding tools, but that is a topic we talk about quite frequently in our sessions. If you'd like to reach out to us and connect with us, we have our website, and I'm going to put some of these links here in the chat here real quick. We have our website where we list all of our upcoming events and stuff like that. We have our LinkedIn page where we, this is where we actually publish out the new events on LinkedIn so people can join. A lot of the recordings and other things from the session get posted up onto YouTube. So if you want to go back and watch the recording from this, you can go check out our YouTube channel. And of course, you can always email us at community@trainingforprogrammers.com. Oops, wrong direction. All right. Our next programmer to programmer training session, so our programmer to programmer series is our free sessions that we offer, is going to be coming up on Friday, August 16th. We're going to take a look at building web applications with Rust, Actix Web, and HTMX. This is going to focus in on a full stack application. So HTMX is a client-side library that has very minimal JavaScript usage, and yet you get many of the same benefits that you'd get with like React or Angular. And then Actix Web is a Rust-powered server-side web framework that we'll be using for the code that runs on the server. And we're going to take a look at how to build web apps to tie all of that together. It'll be a 2-hour session approximately, and we'll be doing that in the middle of August. Okay. Couple of things here. Number one, thank you for registering and attending. Number two, review the demos from the training session. So when the training session is over, you'll have full access to the source code. Go back and take a look at them. If you have any additional questions, feel free to reach out to us on Discord. You can get the link to Discord when you fill out the survey at the end of the session. So at the end of the session, you'll get an email. And then from that email, you can click the link to join Discord, and you can ask questions and stuff about the session even after it's over. Within 72 hours of the event, the recording will be available. We'll also be sending you a badge for attending. So the badge will come to you as an email message. For the recording link, just come back to the Training for Programmers website, and you'll see the link to the recording, or just go to the YouTube channel, okay? We're not actually using Eventbrite anymore. I keep forgetting to take that out, but definitely follow us on LinkedIn for future events. And then, like I said, we'll have an end of session survey. On that survey, you'll get a link to the Discord group if you'd like to join to ask further questions. Okay, let's go ahead and talk briefly here about Rust, and then briefly about how we connect Python into Rust, and then we'll get into the coding. So first of all, Rust is a memory-safe, fast concurrent systems programming language. It is quite often used as an alternative to C++ or even C. Rust is not garbage collected, just like C++ and C are not garbage collected. They're it's part of a family of languages where memory is managed manually. The problem with managing memory manually is it's easy to make a lot of mistakes, like memory leaks and things like that. Rust solves that problem by basically enforcing memory safety at compile time, as opposed to garbage collected languages that enforce memory safety at runtime. So Rust is all about being memory safe, but it's enforced by the compiler when you compile your code. It is a systems level programming language, so you can use it to contribute to the Linux kernel. You can also use it to build web applications, so on and so forth. Its memory safe mechanism with the compiler is called the borrow checker. And basically, Rust has this unique ownership model to help you manage memory correctly, to understand who owns what data, who can change it, who can read it, so on and so forth. It has a powerful type safety system and error handling features. Error handling is actually really cool with Rust. It treats errors as values as opposed to exceptions that are thrown. And it forces you to really handle those errors in your code. You just can't simply ignore them. It supports zero cost abstractions, so you don't experience any performance penalties when you're using high level features. And as I just mentioned, it's used for a whole variety of purposes. So the goal of this session is to talk about how we integrate Python and Rust together. So one of our first sessions we ever did, we did a class on Rust for Python programmers, and that was where people who knew Python leveraged Python knowledge to learn Rust. This is kind of like the follow-on to that class. This is how do I use Rust as a Python programmer to build extensions that are super fast, can leverage the capabilities of my system much more than Python can. How do I build those extensions in Rust and then call them from Python? So to really succeed with this, you have to know Python because you'll be using Python to call the Rust code, but you also have to know Rust because you'll be writing these extensions in Rust. To put all this together, we're going to use a tool or a library or framework really called Pyo3. Pyo3 is the framework that's used to put these two things together. It provides the Rust bindings for Python and including tools for creating native Python extension modules. In fact, that's what we're going to be focused in on here today. We're going to be writing code in Rust and calling it from Python. However, it also supports running and interacting with Python code from a Rust binary as well. We're not going to be doing that as part of the session. We're not going to be calling Python from Rust, but that's kind of the opposite side. And you can also do that with Pyo3. It's really cool. It provides automatic type conversion from Rust to Python and Python to Rust. We'll take a look at that. It supports async and await and adds parallelism to Python through the Rust extension. We'll take a look at how that works. As you know, with Python, the big limitation for multi-threaded programming is the GIL, the global interpreter lock. By writing our extensions in Rust, we can escape the limitation of the GIL, do the processing that we need to do, and then return the results back to Python and make use of it. It does support things like Python classes and Python error handling, right? So the reason why I highlighted those two things was Rust is very different from Python. So Python has classes and is used for object-oriented programming. Rust does not have classes. Rust is not an object-oriented language. Python uses traditional exception handling, right, with try except blocks and raising or throwing exceptions. Rust does not handle exceptions that way. It treats errors as values and has a totally different mechanism and concept behind error handling. Yet Pyo3 is going to allow us to put these different languages together in a way that makes sense and is actually pretty easy to use. So that's what we're going to be taking a look at here today as well as part of the code we're going to be going through. So let's go ahead. I have Leptos on there still. I should say let's program in Rust and Pyo3. That's okay. We're going to be jumping into Pyo3, not Leptos. All right, so let's get started here. I'm going to give you the link here to our repository. And actually, hold on one second here. Give me one moment. I'm going to make it public. I thought I had already made it public, but I did not. Let me change that to public real quick. Perfect. Okay. All right, so now our repository is public. Let me go ahead and drop the link here into the chat for you. All right, so if you have a public GitHub account, what I recommend you do is the following. Load up this link in your browser. Make sure you're logged into your public GitHub account, public personal GitHub account. Fork the repository. Once you fork it, come under code and create a code space. Okay. So you're going to take that link, put it in your browser, make sure you're logged into GitHub, fork the repository. Then on your fork, don't create the code space off the T for P community one, because you won't be able to commit your changes. Create the fork, and then off the fork, create the code space. Okay, you should see a green button that says, create code space. The code space, as long as you haven't used up your 120 free hours from GitHub, you'll have more than enough free code space hours for our 2-hour session here. So you can use that for free from GitHub for up to 120 hours. Anyways, I'll give you a second to go ahead and fork that and create the code space. I know that the big exciting news in the tech world right now is the Microsoft outage and CrowdStrike and stuff like that. Last night, as part of that Microsoft outage, GitHub was also having outages. One of those outages was code spaces, but I've been using code spaces all morning doing some last minute preparation for this. And I didn't have any problems with the code spaces. So your code spaces should load up okay for you. I'm going to go ahead and restart my code space here real quick. Now I'm going to do most of the coding here in the code space. When we get to the parallel part, I'm going to switch to my local machine where I have more CPU capacity available to demonstrate the parallel code than what the code space is really going to give us. But all of the demos, everything, all of it works in the code space. I tried it. Everything should work fine for you. All right, let me take you on a quick tour here of our project setup, just so you're kind of aware of how this is all set up here. In our project, you'll see a root level cargo toml file. This is the workspace cargo toml that basically links to the 4 demos that I have: Pi Hello World, type conversion traits, parallelism, and async. In order for the Rust analyzer and for cargo and Rust to work properly for our overall project, I have to have this cargo toml that references these individual projects here. You will notice that each individual project also has a cargo toml file. Okay. When we talk about the cargo toml, there's one at the workspace level. There's also one for each individual project too. Just kind of keep that in mind as I talk about cargo tomls. We have 4 demonstrations. We're going to walk through all 4 of them and talk about them, so on and so forth. However, I want to mention to you that each demonstration has a README file in it. This README file walks you through the steps of how to run each demo. And we're going to be using this README file as I walk through and do this. But just so you know, when you go offline after the session is over and you want to practice some of this, maybe on your own local machine, what have you, you can come back to these README files inside of each project, and you can see the instructions for running this. And I've gone through and double checked and verified these this morning to make sure that everything lined up here with the code space. As long as you've got Python and Rust installed on your local machine, these instructions should work. The one thing I will mention to you is this is the activation command for Linux and Mac. If you're on Windows, you'll have to activate it on Windows using either the PowerShell or DOS command prompt approach, okay? But that's the only thing that's really specific here to Linux is this command right here. Okay, before we dive into the code, I'm going to take you over to the Pi03 documentation, and I'm going to show you kind of the hello world instructions they have to get up and running with it. So if you want to create your own extension, you have the ability to do that. So this is the Pi03 GitHub site. I'll put that into the chat for you. Down here, it's got some descriptions and explanations, and it's got the little tutorial on how to get up and running. But there's also an official user guide and API documentation. So the official user guide looks like this. The API documentation looks like this. So you know in the Rust world, right, we have kind of what you might think of as the book. That's more like an actual user manual. And then we have this page, which is kind of like the API details of all the little language features inside of a given crate. So we'll be focusing most of our time on the book side of it. But if you're looking for the API details, it has one of these sites as well. Okay, so what we want to do is we want to create our own little kind of hello world extension so you can see how basically I created each of these demos before I then put my own code in them. Now, this first demo, the hello world demo, literally is just the hello world that it has you do as part of the documentation. So after we create our own extension together, we're going to go ahead and move on to the second demo. Okay. All right. So with that said, what I'd like you to do is go ahead and open a terminal window here in your, I'm going to move this one out of the way because I'll end up typing in the wrong window. Go ahead and open a terminal window. If you're not sure how to do that, inside of the code spaces, it uses VS Code, because VS Code is actually a web page. Even the VS Code you use local on your computer is really just a web page running inside of a Chromium browser. So on code spaces, it uses VS Code. If you click on the little sandwich menu here and go to Terminal, New Terminal, it'll bring up a terminal like this. Now, your terminal window is probably going to look a little different in the terminal window itself. I threw a little configuration into my bash RC file so it would look a little bit nicer. But don't worry about it if your terminal window looks different. It doesn't make a difference. Just type in all the same commands that I'm going to be typing in. Okay, so what I want to do is I want to create my own initial project. So if you come back over to the documentation here and you scroll down, okay, it's going to have some steps that we walk through to do that. Here's the thing. Before we can run these steps, we have to first create a folder, set up a virtual environment, activate it, and then install a tool called Maturin. Now, don't jump ahead and run these commands because we're going to have to install a particular version of Maturin for what we're using for today's demonstration. So what we're going to do is we're going to come back over to here, and let's start by creating a folder, and we're going to call this 00 Pi Rust welcome. So we'll call it make directory. In fact, before you make it there, let's actually go into the demos folder so it stays nice and neat. So we'll say make directory 00 Pi Rust welcome. So I'll go ahead and create that folder. You'll see the folder now shows up over here on the side. I'm now going to change into that folder. The next step I need to do is I need to create a virtual environment. I'm going to type clear here just to clear the terminal to make it a little easier to see. And I'm going to type in Python -m venv venv. So Python -m means we're running a module. The module we're going to be running is the virtual environment module that comes built into Python 3. And then venv is the name of the folder that we're going to store the virtual environment in. So we're going to use the virtual environment venv module to install a virtual environment inside of a venv folder. That's why you see the word venv twice. Once I go ahead and create that virtual environment, you'll now notice that under Rust Welcome, there's a venv folder, and inside of that folder is the virtual environment that was created. I'm going to type in source venv bin activate. Since we're on a code space on Linux, this is the command that you would use to activate that environment. So we'll go ahead and activate this. And you can see our environment here has come to life. Now that I've got the environment activated, I need to install the Maturin tool. If you do the command here and just say pip install, the problem with that is it's going to install like the absolute newest version, which won't necessarily be compatible with the little demos that we're going to do here. So we're going to install version 1.5.1. If I come back over to my README file here, I actually have the command that you need to run to install that for particularly 1.5.1. I'm going to copy that command. I'm going to come back over to my folder where my virtual environment is active. I'm going to paste that. And I'll go ahead and install Maturin. So once you've created the folder, create the virtual environment, activate the virtual environment, then you can install Maturin. After we do that, our next step is to come back over to these instructions, and we can now go through the process of creating our little project. And we're going to do that with the command Maturin init. So Maturin init is going to create all the things we need inside that folder to start building these Python extensions. So I'm going to copy this command. I'm going to come back over to here, and I'm going to paste it. Now keep in mind, I created a folder, created a virtual environment in the folder, activated the environment, and installed Maturin 1.5.1. Those are the steps that we did. Now we're going to initialize our project. When I go to initialize the project, package names cannot start with a digit. So here's what we're going to do. I'm going to go up a folder, and just temporarily, I'm going to move this to be Py Rust Welcome. So just move that folder to that name right there and get rid of the 00. I'll go back and add the 00 later to keep the folder organized. But go ahead and just move that folder. And then once you do that, you can change back into it. And then you'll be able to run the command. I always forget that that Maturin won't allow me to have a 00 there at the beginning. So go ahead and move that folder, then cd into it, and then we're going to do a Maturin init. I'm going to raise this up a little bit so you can see more of the command history, and I'm going to run Maturin init. And I got to fix my virtual environment, of course. Sorry about that, everybody. So let me do this. I'm going to come into here and I'm going to python -m pip uninstall Maturin. And yeah, I'm just going to remove the virtual environment. So let's deactivate. Let's remove the virtual environment. Sorry about that. So go ahead, deactivate, remove the virtual environment. We'll create it again, and then hopefully our paths will all line up. Note to self, don't put a 00 at the start of the parent folder name. All right, so we'll come into here, and I'm going to create that virtual environment again. Then I'm going to activate my virtual environment again. Then I'm going to install my Maturin. And then I'm going to run Maturin init. Hey, look at that. Now it finally works. Okay. The bindings that we want to use here are pi03. So go ahead and select the pi03 bindings. And then it will complete our initialization. And then underneath our pi rust welcome, you'll see these are the files that we created. So I'll pause for a second, let you run that real quick if you're coding along. Now, the next step we need to do before we start doing any coding is we need to connect this project into our workspace. So how am I going to do that? I'm going to go up a folder and I'm going to say move pi rust welcome to 00 pi rust welcome. So go ahead and go up a folder back into demos and go ahead and move that over. So now you should have folders that look like this. Once you've done that, we need to update the cargo toml for the workspace, not the cargo toml for the individual projects, but the cargo toml for the workspace. So I'll come back over to the cargo toml for the workspace, and I'm going to add a new member up here at the top called pi rust welcome. So when it's all said and done, we created a pi rust welcome folder, created a virtual environment, activated it, installed Maturin 151, did Maturin init. I then renamed the folder to the 00 and then added it to the cargo toml for the workspace. This is the root level cargo toml. Now that we've done that, the Rust analyzer and our Rust tooling now know about this project. And so everything will work for us. Next step in the process. Let's explore what was created here. So first of all, you're going to see a GitHub workflow for basically doing some build automation. We're not going to be taking a look at that as part of our session today, but it does come with a workflow that you can use if you want to have an automated build server to build your extension for any number of different platforms. There is a source folder that has some Rust code. This Rust code here is the actual Rust code that's going to be the Python extension, and we're going to be able to call this function sum as string from our Python code. We'll take a closer look at the syntax here shortly, but for right now, just understand this is the actual extension, and this is the code that we're going to be able to call. If any of you all have ever done any C extensions for Python, if you look at that C code compared to this is much neater and cleaner than the C code that you would use in a C extension. A gitignore file was created, so we have good maintenance of our project. A cargo toml file was created. This is the actual name of our package. Version, we're using the 2021 edition of Rust. This is going to set up our code as a library and make our compiled Rust code available as a C dynamic library to Python. That's what the crate type here is for. And Py03, this is the actual Py03 that we're using to connect the Rust code into Python. There's also a project toml file here. This is going to have the information necessary for Python for putting this package together. So the PyProject toml is for the Python package we're going to create. The cargo toml is for the Rust code for doing the building of the Rust application, which then gets packaged up as a Python package into an actual wheel file. Okay, just a quick little overview of what that looks like. Now, how would I actually go about building this code and then running it and seeing it in action? Keep in mind, our goal is to run this from Python, but the code is written in Rust. So the first step is we have to compile the Rust code. The second step is it has to be packaged as a Python package. The third step is the package has to be installed. The reason we're using Maturin is Maturin makes this very easy to do. All I have to type is Maturin dev. When I run Maturin dev, make sure you're in the right folder. Let me change into the 00 again. When I run Maturin dev, it's going to build the Rust code, create the package, and install it in my Python virtual environment. I can then use the Python REPL environment, the read, evaluate, print loop environment, to actually import this code and be able to run it. So I'm going to say Maturin dev, and boy, it really doesn't like my renaming of things, does it? Hold on one second. I've never had this happen before where it actually uses the full path and it can't find it. What I'm going to do, I apologize for this. This was not planned. I'm just going to put this back to PyRust welcome. And we'll move this back to here. Because I'm going to get rid of the 00, I have to update the workspace cargo toml file like that. Now, if I go back into PyRust welcome, I should be able to say Maturin dev and everything builds. So sorry about that. Just update the folder there to be without the 00 and make sure you update the cargo workspace. Okay. Once you update that, you'll see that it's able to build. So it builds our extension. Then once it builds our extension, it installs the extension. So what I have the ability to do now is I can come into here and say Python. I can then say from, and this is going to be called PyRust welcome. from PyRust welcome, import, and I'm going to do sum as string. So from PyRust welcome, import sum as string. And then if I come in here and do sum as string, I'm going to pass two numbers to it and add them together and return them as a string. So I'll say sum as string 1, 2, and I get back a string of 3. So this ran the code up here that you see. Okay. So we compiled it, created a package, installed the package, then fired up the Python REPL environment. We were able to import that, and then we were able to run the code there. Now, that is a dev version. That is a dev version of the package we've created. It is worth mentioning to everyone, the development build of the Python extension, the development build, has a bunch of debug stuff added to it, and it's slow. So the debug build of the Rust application is going to be slow relative to the production build of the Rust application. So how would we go about producing the production version? So I'm going to come into here and I'm going to exit out of the REPL environment. I'm also going to come in and uninstall the dev version of the extension that we just installed via Maturin Dev. So I uninstalled that. After I uninstall that, now what I want to do is I want to do a release build. So I'm going to say Maturin build release. This will actually do a production build of the Rust code and create an extension or a Python package that has that code in the package. So if I run that, it's doing the release build. Because it's a release build, it's not going to automatically install the extension for me. So here you can see where it built the wheel, okay? And there's the path to the wheel file. What I can do is copy that, and I can say python-m pip install, and I can paste the actual path to the wheel into here, and then I can run it. And you can see now it has installed the production version of the package. In this example, you're not going to notice a speed difference, right? We're just calling a single function and adding two numbers together and returning a string. However, when we get over to the parallel side, you're going to see there's a big difference in performance between the debug version of Rust and the production build of Rust. So now if I come back into here and bring up my Python REPL environment, I can import that, run my code, and it's running the production version. Okay, so that's our little welcome application using the standard installation instructions. And once again, I apologize for the frustration with the 00 in the directory name. I'll have to go back and rework that part of my initial demonstration. With that said, though, let's take a look at demonstrations 2, 3, and 4, because these are going to introduce some of the things that you need to know about if you want to start being productive with Py-O3 and Rust in building these Py extensions following today's session. So let's go ahead and come on over to the Py type conversion traits. Now what we're going to do is we're going to create a virtual environment activate it, install Maturin. We're going to repeat that process for each demo because each demo will have its own virtual environment. Here's the thing though. Maturin is not going to complain because I've already created the project. The project already has a name that doesn't have 00 or 01 or 02 at the front. We're not going to run into any of those issues we ran into just kind of creating one on the fly. So let's come into the O2 folder. So I'm going to go up a folder and go to O2. And we're simply just going to copy and paste these instructions here very quickly. I'm going to create my virtual environment. And for these next demos, I'm just going to do this in rapid fire, so to speak, to then activate the environment, to then install Maturin in the environment, to then going ahead and building the project. So I'll paste that in there and go ahead and let that build. Feel free to do the same on your side if you'd like. Okay, you can see it built it. It went ahead and installed PyType conversion traits. Unlike the previous demo where I fired up a REPL environment, in this demonstration, I have a file called app.py, and app.py is going to be pulling this package in, this module in, and then we're going to be making use of it in a regular Python file. So this would be what it would look like if you were doing like a real program. You'd go off and build your extension, get your wheel file, go to whatever Python project you're working on, install the wheel file, and then you would just write regular Python code, importing the extension and making use of it. Now, before we get into the details of what's happening here, let's actually take a look here at the app.py and the librs. Let's take a look here at this add function. This is the add function as implemented in the Rust code, okay? Now, if I mouse over the add, you'll notice I have type hints. For those of you who have used type hints in Python, you know that it adds static typing. It makes Python, in my opinion, a more enjoyable programming experience because I actually know what the parameters are, what the return types are, stuff like that for functions, as well as the type definitions of other variables and such. These type definitions did not come from the Rust code. Yes, the Rust code is statically typed and strongly typed because Rust is a statically and strongly typed language. But the type definitions over here from Rust did not somehow magically appear over here on the Python side and be integrated with MyPy and stuff like that. To get the type definitions, I had to create a separate PyI file where I defined my type definitions for the code in my Rust files. So I did have to do this extra step here in order to get nice, friendly type definitions here that translate to the equivalent type over in Rust. So I wanted to point that out real quick, that there was an extra step that I had to go through to get that static typing inside my my Python code with the type hints, and that was the creation of this file. So with that said, let's go ahead and let's take a look at the code that we're going to be calling it from with Python and the implementation of it on the other side over in Rust. So one of the challenges that we have in integrating Python with C or with integrating Python with Rust is that everything in Python is an object. What does that mean? I'm sure you've heard that phrase before, but what exactly does that mean? What that means is that every value or structure. Think of a value as like a number, maybe a structure is like an instance of a class, whatever. Every value or structure is an object in Python. And what that really means is that every value or structure is a PyObject type in C. So the Python that we all use is commonly called CPython because it's actually implemented in the C language. Traditionally, if you wrote extensions, you had to write them in C. If you were to look at C programming code for Python, you would notice that everything is a PyObject type. For example, let me do this here real quick. I'm going to fire up Copilot and ask Copilot to write some code for me. Write a Python C extension that has a function that adds two numbers together and returns the sum. One nice thing about Copilot and Python C extensions, you get actually really a lot of great help in Copilot on how to do that. We'll give it a second here to create this. Okay, you can probably start to see some similarity here with the Rust code. See how we have this function here for add numbers. We have an add function there. If you scroll down in the earlier example, remember how we had the Py module to do things like register the function? In a C extension, it would look like this. So there's the add numbers. This is where I register add numbers with the module. And then I've got other code here that also does module initialization. This is what you'd have to do in C. Well, you will notice that the actual inputs for the add numbers function is called a PyObject, actual type of PyObject. So no matter what you pass into the add function, it will always be interpreted as a PyObject because these are PyObjects in C and in Python. So here's our challenge. In order for me to add these two numbers, what do I have to do? I have to extract their value out of the PyObject to then be able to do the add operation. In C extensions for Python, you do that by using this function here called parse tuple. And basically you give it the args that you received. So there's the args that are pyarg. And from the args here, we're going to parse out the two numbers that we receive and then have access to A and B. So the arguments come in here as the second parameter. The arguments are actually a tuple, which is a PyObject. We parse from the tuple the two numbers that we're going to do the add operation with. Do you see how inefficient this is? Python's a fantastic language, but because it's so dynamic and things are stored as these PyObjects, to do any type of operation requires you to interrogate the PyObject to get the data out. Well, all of this is also true for the Rust extension, right? Just because I'm using Rust, it doesn't mean PyObjects go away. It doesn't mean that we don't have to figure out what things are. But here's the cool thing with Rust. With Rust and Py03, it handles all of these little details for you. You see this macro right here that we're applying to our add function? This Py function macro is taking care of all of this kind of stuff for us. We don't have to write the code to do all that. What Pio3 is going to do, it's going to take the Pi objects that we receive, and it's going to convert that data into two parameters, A and B, of type float64. Isn't that cool? So Pio3 handles that for us automatically. If you go over to the documentation here and you go under type conversions, mapping of Rust types to Python types, it'll actually tell you what the Python type is and what you can convert it to over here in Rust. And this is the actual C type of that type if you were doing like C extensions. So anyways, I'm sorry, this is the Rust type equivalent to the Python native. That's what I meant to say. So anyways, I can take a float or an int and it can be converted to these values over here. So if we come back over to our code, I'm going to pass in 1 and 2. Because it's going to do all that conversion stuff for me, my Python function is going to receive A and B without us having to do all of this work. And that's taken care of here for us by our Pi function. Now, the return value here has to be of type Pi result. So if you take a look down here in the add numbers, when we return the result of adding, notice it has to be wrapped back up in a Pi object. It has to be wrapped back up in a Pi object. Well, here, we don't wrap it back up in a Pi object. We take our result and return it as a Pi result, and we let Pio3 handle all of this conversion for us to then send that back. And we don't have to worry about it. Okay. So that's kind of what Pio3 is doing for us. It's eliminating a lot of the boilerplate that you would see in a traditional C extension. It's also handling that automatic conversion from one type to another, and we don't have to write the code to do that. So let's take a look at some more examples here of how this is going to work for these different types of data. So here I have a list of numbers. I want to call map float. It's basically going to receive a lambda function, the list of numbers, and I want to get the double nums back, and I want to view the type. Over here, we're going to have this map float. The transformation function is going to come in as a reference to this type called pi_any. We also have our list here. So it's going to receive the lambda as the pi_any, but it's actually going to take the Python list and convert this over to a vector of F64s. Now, of course, you have to make sure that the Python list you're passing in is only a list of floats. If you start combining different data types like you're allowed to do in Python, that conversion isn't going to work when calling the Rust code. Now, once I receive that list, what I want to do is iterate over it, and I want to transform each item and then push it onto my new list and return back the new list, right? So I have a Pi result of a vec64, F64, and then I'm going to be returning that right there. So this is what it looks like to actually call this lambda function. I'll say pi transform func.call1. I'm going to pass in a tuple. Remember how we saw over here that in Python, really all the functions receive a tuple of arguments. When you pass in a bunch of different arguments into a function, that's converted into a tuple. and then that tuple is processed inside the function to get out the actual data values. Well, we're going to create a tuple, pass in the item, which is the item we're iterating over the moment at that moment in the list. It's going to call the function and give us back a pi any. Off of that pi any, I'm going to extract the data from it. Remember, this function is defined in Python. So when that function runs, it doesn't return back to me like a Rust data value. It returns back to me one of these Python objects that I then have to go in and extract the data on. Now, the cool thing is in Rust, it knows what type of data I'm extracting based upon the type definition of this variable. So I don't have to explicitly tell extract that it's an F64. Extract knows that it's an F64 because Rust has the ability to look at this type definition and then infer that that's the type that we're going to be extracting here. Now, let's take a look at example number 3. We're going to pass a dictionary, and then we're going to get back a tuple of lists. So we'll have a list of color names and a list of color hex codes. Okay. So what is that going to look like over here? Well, in Rust, the equivalent of a dictionary is a hash map. So as long as I have my pi function decorating the method and it's able to do that translation between types, I'm going to receive my dictionary as a hash map, and then down here I'm going to create 2 vectors, one to hold the keys, one to hold the values. I'll iterate over my hash map, getting each key and value, pushing them onto the vector, and then we're returning back a tuple of 2 vectors. That tuple can then be unpacked over here in my Python code, and I can print those out. We'll run all of this in a moment, but I want to just look at the code here. What about working with dates? Well, Rust doesn't have a built-in date type. You have to use a package called chrono. Chrono is going to give us our date time, and that's what Pio3 is looking for. If you've got the chrono package installed, it'll do that translation of the date time objects from Python into the chrono types. So up here at the top here, I've got chrono being brought in. Also, too, it's worth mentioning that in my cargo toml, you'll see chrono is listed as a dependency of the extension. So down here, when I call get weekdays, I have 2 date objects. They get converted to native dates. And then I have my code here doing the processing, giving us back the weekdays between January 1st, 2021 and January 31st, 2021. So I'm not so much interested in the logic here per se, just this idea of using chrono to be able to convert that Python date object over to a native date. Now, this next one's kind of interesting. What if I want to create a class definition inside of Rust and use that class definition in my Python code? Well, I can apply the PyClass macro to a struct called point here. Struct point is just a tuple struct in Rust. And then using an impl block, I can apply the PyMethods macro and make these methods of this Python class I'm constructing. Now remember, Rust has no concept of classes, but Pio3 is going to use what Rust does have, structs and implementation blocks, and utilize them together to give us the equivalent of a class over here in Python. So if we take a look at this, you'll see that I'm going to mark this as my dunder init. And then down here, here is a method. You'll also notice that I'm receiving a reference to self. If you've ever used impl blocks before, you know that in Rust we have that self variable. I'm going to receive a reference, do my math operations, okay? Remember, it's a tuple struct, so this is referencing the first element of the tuple, the second element of the tuple, so on and so forth. And so I'm going to come into here and create 2 points, and then calculate the distance between them and print it out. Now, if I scroll down to here, you'll see where I have to register the class differently than how I register functions. So you do have to register the class there as part of your module. Then finally, we have our person here. This has actual named fields. It's not a tuple. So I have first name and last name. And then down here, I have my code for creating it, the dunder init. And then I've got my full name down here, returning back the printing of that full name. So if we were to come into here and do Maturin dev, so it installed it for me. And then if I say Python app.py, there's the output from the code. You can see class float, class list. I'm getting actual Python types back, just like you would expect in a Python program. Py03 is translating all of that for us. Okay, so let's take a look now at the reason why you would even consider doing a Rust extension for Python. Sure, Rust extensions are awesome, but it's a lot of extra work and you have to know Rust. So you would only go and create a Rust extension if there's something that Rust can do better for you than what Python can do. Essentially, if you need to run some type of operation that is CPU bound, where you need to leverage multiple cores or multiple CPUs, that's where Rust starts to shine, as opposed to implementing a pure Python solution. Rust is going to let you escape Python's global interpreter lock and allow you to really leverage the computing resources of your machine to do things much faster than what you would be able to do in ordinary Python. Okay. Remember, in Python, because of the GIL, there's no thread-based parallelization. The only way you can really do things in parallel in Python, pure Python, is through multiprocessing. But remember, multiprocessing is inefficient relative to multiple threads, right? So if I really want to speed things up and get lower level access to the system, I have to kind of escape Python and escape the GIL. A C extension is one way to do that. A Rust extension is also a way to do that. So let's take a look here at our parallelism examples. We're going to run some benchmark tests and stuff, and then I'm going to run it locally on my machine so you can see the results on my local machine. So first of all, everything here pretty much looks the same, except we did make one structure change. Up here in the PyType conversion traits, we had a source and a lib RS folder, and that was it. And then we had this PyI file for the type definitions of the librs code. In that case, the extension that we built was purely Rust. However, it is possible to build extensions that are a mix of Rust and Python. PyParallelism, this example, is going to be a mix of Rust code, but also a mix of regular Python code. So what you see here is I'm importing all the methods from the Rust code, and then I also have an implementation of one of the methods in plain Python code. Okay. So this enables me to write part of the extension in Rust, but also part of the extension in Python. When you have an extension that has both languages, you need first to create another folder called, in this case, PyParallelism, but the name of the extension. You can put your Python files in this folder, and the PyI file goes in this folder as well. So here, the PyI file was right here at the top level project folder. But here, when I have a mix of Python and a mix of Rust, I move the PyI file into here. So this is plain Python code. This is importing into my module that I'm creating the Rust code that we're building as part of the extension as well. The Rust code is here inside of librs. Let's take a quick look here at the Rust code, and then we'll take a look at how to create the environment and all that and get everything up and running. Essentially, what we're going to be doing here is we're going to be taking a bunch of text. So this is the Zen of Python. We're going to multiply this text by 1,000. So we're going to just basically take this text and copy it 1,000 times. We are then going to go in and search. Actually, not search. We're going to do a word count. We're going to just search the text for a word and count the number of times that word appears. Okay. So we're going to search the text for a word, count the number of times it appears, but we're not just doing it in one copy of the Zen of Python. We're doing it in 1,000 copies of the Zen of Python. So when you look at this code here, you'll see I've got a Rust function, just a plain Rust function, that receives a string slice for the line that I'm searching, the haystack, if you want to call it that. I have the needle that I'm searching for as a string slice, and we're going to split on the space, iterate over the results of the split, and compare the word to the needle. If it equals, we'll go ahead and increment the total by 1, and then we return the total here at the end. So all this function does is just receive a string slice and count the number of occurrences of the needle in the slice. We're going to use this function in all of the functions that you see below. Okay. Now, I've got a total of 6 functions. So we have our Py module at the bottom, but I've got a total of 6 functions. Let me show you how they're paired together. I have a version of the function that searches the text sequentially. So it starts at the very top of the first Zen of Python and sequentially searches all the lines, one line after the other. Okay, one line after the other, looking for the needle and counting. I have a version called Search Parallel. Search Parallel makes use of a crate called Rayon. Rayon basically allows me to search the text in a parallel kind of way without me having to write any of the parallel code. So it's an easy way to parallelize an iteration scenario without having to do a lot of work. So when you see here and I say search parallel, this search parallel is just using par lines provided by Rayon to parallelize the search for the needle. The last version is one where I do my own multi-threading. And so you can see it gets a lot more complicated here because I'm having to track data across threads and stuff like that. But I do my own multi-threading and accomplish the same thing. Now, on each thread, I'm using the Rayon library. Okay, so on each thread, I'm making use of the Rayon library as well. Okay. Now, down here, you'll notice there's a second function for each of these. When you call your code from Python, the Rust code can keep a hold of the GIL, or it can release the GIL. If your Python code, or if your Rust code does not need the Python interpreter to execute at all, it can release the GIL, allowing the Python interpreter to go off and do other stuff while it finishes doing whatever processing it's going to be doing. Okay, so we're going to release the GIL. Where releasing the GIL is helpful is not really in a single threaded application, because in a single threaded application, you have to wait for the results to come back anyways. But if you had a multi-threaded Python application or an asynchronous Python application, and you can release the GIL, it allows Python to go work with those other threads. Okay, it can go work with those other threads. So let's take a look here. Let's take a look here at how we're going to call these functions. So I'm going to come over to here. I have a test folder, and I have a Python file here that has the text and a bunch of tests. Now what I'm going to do is I have the test kind of broken into two categories. I have a bunch of variations we're going to look at in a little bit. But up here, I got some basic tests where we're going to look at testing the word count Python sequential release GIL, parallel release GIL, threads, and threads release GIL. So all those same combinations we saw before. Also, I have a version that just uses plain Python, no Rust. The plain Python would be like the way you would write the code if you were just writing plain Python code. Let's say you decide the plain Python code is too slow. That's when you decide to jump over to write the extension in Rust. Now, let's run this in debug mode, and then let's run this in production mode, and let's take a look at the comparison of the results. To do this, I'm going to need my terminal window. I'm going to need to change into my demos PyParallelism. I now need to set up my environment. Now this one is slightly different. We're still going to have a virtual environment like we did before. So I'll create that. I'm still going to activate that environment like I did before. So I'll paste that. However, I'm going to be installing Maturin plus 2 additional packages, PyTest and PyTest Benchmark. And I'll go ahead and paste that. Now I can run Maturin dev, and I can run PyTest to actually run the tests. Now I'm going to collapse that down. I'm going to run Maturin dev. We'll let that build the development version and install it. I'm now going to run the test here to run this whole benchmark mechanism. So I'm going to fire this off, and it's going to run. It's like a whole benchmarking tool here. And we'll give it a second to execute. Now, we're not going to look at all the stats. I'm really just going to focus in on the mean. So the mean is the average time it took to run. So when you use a benchmarking tool, it usually runs it many times. Although in this case, I think it must have only done one iteration, but usually it will do many times.
and it'll give you the average. So if you take a look here, the best performing version was actually Python. The best performing was not Rust at all. So if you look at these initial results, you'll see Python going super fast relative to Rust. And you'll be like, Eric, why did I even spend the last hour and 20 minutes sitting through this if Python is faster? Why did I deal with all of that 00_pi Rust welcome stuff if in the end Python is faster? All right, well, let's run this as a production build. Remember, we didn't run this as a production build. So I'm going to say Python -m pip uninstall, and the name of our package here was, let's see, PyParallelism. So I'll uninstall that. Then what I'm going to do is, instead of saying material and dev, I'm going to do build release. Of course, once I do the build release, I have to manually install that. So we'll come into here and say install. Remember, you can get the full path to the wheel right up here. So I'll copy the wheel file and paste it. Now I'm going to run my test again. And let's see what our results look like. Yeah, that Rust is a lot faster now, isn't it? Look at that Rust sequential release GIL. I'm sorry, the Rust sequential, this one here, the mean is the fastest. So the regular Rust sequential here was the fastest. Why was it a little faster than releasing the GIL? Because releasing the GIL is like an extra step. Our code in this case didn't really benefit from doing that. So it took slightly longer to release it. If we were doing more multi-threading and stuff like that on the Python side, then releasing the GIL would have been more beneficial. But just simply letting Rust do the sequential here, it was the fastest. Well, what happened with this Rust parallel part? This didn't seem to go any faster. I expect the reason for the Rust parallel not really being any faster is either going to be because of the machine that we're on only having 2 cores. Plus, there's also overhead associated with doing it in parallel. So ultimately, parallelization can make things faster, but there's overhead with it. In this case here, the Rust sequential ended up proving to be the fastest. Now look how fast it is compared to regular Python. When we did the non-debug build, regular Python was the fastest. But when we did the production build, regular Python is 5.5 times slower than Rust. Think about that for a moment. Think about all that Python code that we write, and think about how much slower that code is than if you were writing it in C or Rust or C++ or something else, right? It goes to show you how slow Python is, right? Now, ordinarily, that's not a big deal because most of the time in Python, if we're doing something CPU intensive, we're using an extension like NumPy or Pandas, or in this case, our own extension, or we're doing something that is IO bound, and IO operations are way slower than Python. So if you're busy waiting for data from a REST API, it doesn't matter how slow Python is. The slow part is waiting for that data. But you can see we got quite a speed performance improvement by going to the production build on that. Now, what we're going to do is we're going to take a look at some more complex variations. But I'm going to do that on my local machine. So if you come into here and we say Python, and I say import OS, and I say os.cpu count, I only have 2 cores on the workspace, on this dev workspace. If I come over to my actual local computer that I have here, if I type in Python and then do import OS and then OS CPU count, mine reports 32 CPUs or 32 cores. I don't really have 32 cores. I have 16 cores, and each core has 2 hyperthreads. Hyperthreading is not executing things simultaneously. So really, I can only do 16 simultaneous operations at a time on my computer, even though it says 32. So what I'm going to do is I'm going to come over to PyParallelism, and I'm going to open up the source here for librs. I'm going to modify this to be 16 so that it will leverage all 16, or when we do the search with threads, it'll basically do this operation 16 times. So literally what's happening here with search with threads is we are repeating that same operation that we did up here in the parallel or the sequential. We're doing that same operation 16 times, but on 16 different threads, which the OS should allocate to the 16 different cores. So that's the modification I'm going to make there. Also in the tests, I believe I should have a 2. But I had a, I guess I didn't. Okay. So now what we're going to do is we're going to, we'll run the original ones that we did before first as kind of a baseline. And then we'll run some of these other variations that I've created. So on my system here, what I'm going to need to do is repeat those operations we had from before. So I'll create my virtual environment. I'm going to activate that environment. I'm going to install these packages. I'm going to skip the actual dev build. We'll just go right to the production build. So I'll go ahead and do my release build. Oh, hold on. You know what? I didn't change in my demo folder, did I? Hold on one second. Let me delete that. Let's change into demo 03. And I'll do that again real quick. Oh, deactivate. You know, it's funny when you think of all the things that can go wrong in like a presentation or whatever, you never really think of the virtual environment as being the thing that's the frustrating part. All right, so now we'll go ahead and do our release build. Especially with Rust, you think all the Rust code, that would be the difficult part, but it's the virtual environments for us today. Okay, so there's my code built. Now what I want to do is I want to run those tests. So I'm going to grab our command up here to run the tests. And let's get a little bit of a baseline here to see what this looks like. Let's see here. Oh, I got to install the module first. Can't forget to do that. And copy the wheel path Okay, now we'll come into here and we'll try that again. All right, let's see. Why did the thread one fail? Let's try that again. That's odd. All right, well, let's take a look here at the other ones that executed. So if you take a look here, my Rust, let me make it a little easier to read. Okay, so once again, in this case, on this system, my Rust parallel release the GIL actually did the best. I imagine on my system, because I have the 16 cores, Rayon was better able to parallelize things than it was on the 2-core container that we're running on in the code space. So the parallel releasing the GIL actually did the best. The parallel keeping the GIL did the second best. The sequential here, oh, I know why it failed. It failed because it took too long to, I know what the problem is. This is the thing that I had wanted to change. If I go back to here, if we go to here, this needs to be 160,000. That's what I was searching for. Because we're running it 16 times, so the actual count is going to be 160,000. Okay, perfect. Good. Let's go back to the code now. Let's actually run this again, get rid of all the red. Okay, so take a look here. My Rust parallel did the best this time. The release the GIL was a little bit slower. Sequential was a lot slower. Bringing that Rayon library, especially on a machine like mine that has these 16 cores available for execution, when it leveraged those 16 cores, look how much faster that was. Look at Python sequential. It's 23 times slower than what we were able to accomplish with the Rust parallel. So it was only 5 times slower on the container. But on a machine with more CPU capacity, it's 23 times slower. That's pretty crazy when you think about it. You know what I mean? Right? Think about how slow Python is. People don't realize how slow it is until you see stuff like this, right? Now, once again, the slowness only matters if it's impacting something. If it's not impacting something in modern computing, we don't really worry too much about wasting CPU cycles. But under enough load, it could be significant. So anyways, you can see how much faster the parallel is with the Rayon. And in this case, not releasing the GIL was a little bit faster. So what I want to do is I've got a couple more little demos of this, and then I want to talk about the async. But before we do that, I am going to ask you, I would love your feedback on today's session, as well as ideas for future sessions that we could do. So I'm going to put a link here to a little survey form in the chat. If you could fill that out before you take off, you don't have to do it right now. You can wait till the end. But if you could fill that out for me before you take off, it would be much appreciated. I know we have about 20 minutes left to go. But if you could fill that out before you go, it'd be appreciated. And in case anybody has to drop off early or joined late, I'll be sending out the emails with the badges for attending later on today. And I'll be uploading the recordings to YouTube. So you can get to the recordings by going to the YouTube channel or by going to the website and then clicking to the channel from there. Also, we have another session coming up in August on using HTMX in Actix Web for building Rust web applications. So if you have an interest in that 2-hour session, go to the website and register. I'll also be sending out emails and LinkedIn postings and stuff. But just in case anybody has to drop off, I wanted to mention that. Let's jump back over to running our code here. All right. So what I want to do is I want to take a look at some of these variations to kind of take a look at how this would execute if we make things, if we parallelize things kind of in certain ways. So for example, let's take a Python sequential search. So if I do a Python sequential search, I conduct the search 4 times. So 4 times back to back to back, no parallelizing. I could also do the Python sequential search 4 times, and then I could fire it up as part of a thread pool executor. So the thread pool executor would use threading on the Python side, not the Rust side. So if I took my Python code and did it back to back to back 4 times, or did the thread pool executor 4 times, what would the results of that look like? So I wanted to try, in this case, this is all sequential. In this case here, I'm trying to do things in parallel. Let's take a look to see how that would work here in our test. So we're going to run all the same ones we had before, but we'll have 2 additional tests that'll pop up in the list, and I'll highlight them. So take a look at the sequential 4 times threaded and the sequential 4 times just plain sequential. Notice how the threaded is actually slower than the sequential. Because searching for the needle in the haystack is CPU intensive, using multi-threading in Python isn't going to make it faster. It's going to make it slower because of the context switching that occurs with the threading on top of just having to do the CPU operation. So you might think to yourself, well, I'm going to make my Python code multi-threaded. It'll make everything faster. Nope. And that's because of the GIL. It's because of the global interpreter lock. We can't parallelize the Python interpreter on multiple threads. You just can't do it. So that's why this code is even slower than just doing it sequentially. All right, well, let's come back over to our test file again. And this is using the just regular, that's the sequential one. Let's take a look here. So if we do the parallel search 4 times, and I'm going to keep the GIL. Okay. So I'm going to do a thread pool executor. So I'm doing the multi-threading here, but each thread is actually going to call into Rust. And then Rust is going to go off and do its thing. But you'll notice I'm keeping the GIL. I'm keeping the GIL. Let's see if this is going to be what the results of this is going to be. So we're still doing it 4 times, but we're doing it in Rust, but we're going to keep the GIL. So if I come into here and I run this code, we have 1 test that we've added, so now it's 10 instead of 9. All right. So I have Rust sequential 4 times with threads keeping the GIL. So if you take a look here, it's 8 times slower than the parallel one we did here. Okay. So each execution, we did it 4 times. So really, I would have expected it to be 4 times slower, not 8 times slower. But we kept the GIL. Let's see if there's a difference now if I release the GIL. So this time, I'm going to do that sequential, okay? And in fact, actually, let me recompare that. So this was search sequential, not search parallel. So if we look at the 4 times keep the GIL, it did it in, what, 4 milliseconds, 4 seconds? Yeah, 4 seconds. So 4 seconds, if I compare that to Rust sequential, keeping the GIL, that's 977. So it's a little bit slower than 4 times with the threads. Actually, and that makes sense if you think about it, because we're doing all the thread context switching. So that adds some overhead to it, but we're keeping the GIL. Now, this time, we're going to do the same operation with the sequential. So, but we're going to do this with releasing the GIL, okay? So to kind of compare this, up here I did sequential in Python 4 times, and then I did multi-threaded on the sequential in Python. Here we've done the sequential in Rust. So we didn't use Rayon in Rust. We just did a regular sequential in Rust, but we did it across the 4 threads. But you'll notice I kept the GIL. So even though the search itself was overall faster each time, it didn't do them in parallel because it took 4 seconds to do what took 1 second to do it once. So if we did it 4 times and it goes from 1 second to 4 seconds, it really wasn't done in parallel. And that's because we kept the GIL. But if I release the GIL, let's take a look at the results now. So now, if I do 4 times but release the GIL, it takes about the same time as doing it once. This is being parallelized. Why was it able to be parallelized? Because this code released the GIL and did not prevent these other threads from being processed by Python. Because each of these released the GIL, Python was able to truly let these run in parallel. Up here, while we did get a faster search, because I held on to the GIL and I didn't release it, these actually executed in sequentially within Python. Because Python had to give the GIL to this one, and then it had to give the GIL to this one, it had to give the GIL to this one. They weren't able to run in parallel. So what was the difference in the actual code in terms of releasing the GIL or not releasing the GIL? If I just call the Python function search sequential directly, just calling a function in the extension holds on to the GIL. However, if I call a function and it uses py.allowThreads and passes this closure function that then calls search sequential this way, this releases the Python GIL. Now, this only works if you don't have to call back into Python, right? So like, for example, that one example where we called the Lambda function back into Python, you can't release the GIL if you're doing that. But here, because Rust had everything that it needed to go off and do its thing, it could release the GIL, really improving performance. Now, releasing the GIL, you didn't notice anything if we just did one operation. But when we did the multi-threading on the Python side, and then the thread, each thread called that extension function, and that extension function released the GIL, then the other Python threads could then execute. and you get the performance advantage. So you can see Rust not only does things faster, but it really opens up the door to running things in parallel. Okay, let's take a look at our last example here. I know we're down to our last 10 minutes. I sincerely appreciate all of you hanging in here until the end and being patient with some of the struggles we had earlier on. I hope seeing this work and seeing the performance improvements makes it worth it to have kind of stuck here all the way to the end to really see what the power of Rust and Python together can really be. Okay, so for PyAsync, one of the cool things is we can connect the asynchronous functionality of Rust into the asynchronous functionality of Python. Now, technically, Rust runs a separate event loop from the Python event loop, but it does allow you to incorporate asynchronous programming in an extension. Many years ago, I tried figuring out how to do the asynchronous stuff in the C extensions, because C doesn't support async and await. I couldn't figure out a way to do it. I couldn't find a tutorial on how to do it. So when I write C extensions for Python, I just can't leverage the async stuff. I'm sure there's a way because there's things like AIO, HTTP, and stuff like that, but I could not figure out how to get it to work. With Rust, though, you can do the asynchronous stuff and tie it into the asynchronous mechanism of Python. So over here, you'll notice that I am doing things like await Rust sleep, await echo param, await print list, await get stock price, so on and so forth. I've got Python code here firing up the async IO event loop. Over here in Rust, we bring in our Tokyo package that we have. That's one of the async runtimes within Rust. And you can connect asynchronous Rust code via Tokyo through Pyo3 and do things like make Rust sleep here, an asynchronous function that you call with await in front of it. So it's a regular Py function, and it's a regular, function here. I still return back a Py result like we did before. But what's going to happen is I'm going to take this async Pyo3 async IO Tokyo module, and I'm going to take a future and basically have it output a Py result. And so here we're going to use Tokyo times sleep, which is an asynchronous sleep timer in Rust. And then I'm going to return back the result, which in this case is none, because we're just waiting for it to sleep. Notice here that I call back into Python with the GIL. This is the callback. I'm calling back into Python, just like you would in an asynchronous type of thing, right? You hand off the asynchronous task to some background thing. When it's done, it calls back into the code. In JavaScript, you see the callbacks plain and clear, traditional promises and callback mechanisms. When you see async and await in the programming language, it kind of hides that callback. It doesn't make it as easy to see, but it's still a callback. And so you can see we're calling back here into Python. Echo parameter, we're simply going to sleep again and then take whatever value we passed in here and just simply return it back. So I'm outputting a value from there. Then over here, I have a print list. So I'm bringing in a list. And then once again, I'm simply going to print this out and then call back into Python. I have a plain method here for extracting price from a web page. And then I've got some code here that will actually go out and get the stock price. So for example, if you wanted to, build some type of Rust extension that, read from the file system or contacted REST APIs or whatever, you could make that mechanism asynchronous, call the code from Python into Rust, and then Rust could go out and get those resources for you, okay? Now, the one thing I want to highlight about this is returning an error. We haven't really talked about error handling. So as you know, in Python, you throw exceptions, but Rust, errors are values that are returned back through something called the result enum. Well, here we have a pi result, and I'm going to say return error. And what I can do is basically create a pi error from whatever error I'm creating. So in this case, it's a stock price error, and there's the error message. And I'm going to return back this error variant populated with the value of a pi error. Well, if we scroll down here, you'll see that I can define a stock price error and build that off of my stock price error pi exception that I'm going to create here using the create exception macro. So if I come down to here, I can say try, and I can have accept stock price error, and that's the actual error variant that's being returned through my result. So let's go ahead and run this one real quick. I'm going to open up our little README here and do a little copy pasting. In order for this one to work, I need to have package config and libssl installed so that I can build everything that I need to be able to call the REST API. So I'm going to paste that into here. We'll install those. Oh, let me do it up here, actually. We'll come back over to here. And I'm going to simply just copy these commands down real quick. While I'm doing that, if you haven't had a chance to fill out the survey yet, now would be a good time to do that while I create the virtual environment and stuff. And remember, all of this stuff stays up on GitHub even after the session is over. So feel free to go in and fork it later if you'd like. Practice with it if you have questions. Just head over to Discord. You can get that Discord link on the thank you page that you get at the end of the survey. And feel free to go ask questions over there. And let me install that. Go ahead and build. And then we'll run the code. Boy, this came in right at 2 hours. It did pretty good here on allocating time. You never know if things are going to go super long or super short. And so go ahead and run that. And so you can see here, there's my stock price. And let me modify the code to actually return the error instead. So I'll rebuild that. And then I'll run it again. It is possible to increase the like the number of cores and stuff like that you have on these code spaces. It just eats up the hours faster. So the more capable container you have running here, the faster your 120 hours get eaten up. But you can see here, there's our stock price error. That comes back right here. And we were able to do that because in the Rust code here, I returned back an error variant of pi result. As part of that, I created a pi error value, and that was then ultimately translated into a thrown exception here in Python. So you can connect the two of those together. So the goal here for our session, take a look at how you can write Python extensions with Rust. We went over a hello world demo. We took a look at conversion between different types, going from Rust to Python and Python to Rust. We also explored the real benefit of using these extensions, and that is parallelism and the ability to do stuff asynchronously. Obviously, if your regular Python code is running perfectly fine for you, it's running, it's doing what it needs to do, incorporating things as a Rust extension is probably unneeded. But especially if you're getting into CPU heavy stuff, there's not existing libraries out there for you to use. You want to create your own. Rust is a great way to do that. And I'll be honest with you, it's way easier to do than doing it with C. Of course, you have to know Rust. If you don't know Rust, you have to learn Rust. But once you know Rust, it's way easier to do it than doing it with C. And Pyo3 is a great library to work with. Anyways, I want to thank you all again for attending today's session. If you have any questions, you're welcome to put them in the chat or the Q&A before we take off here. Otherwise, you can ask questions over in Discord, and happy to discuss over there. And definitely take a look at the code space here and do some exploring of this on your own. You can see, except for the issue of the 00 prefix, everything worked. So you can go through, follow the README, and kind of explore this on your own, and then try setting up your own local environment if you want. Okay. All right, everyone, that's pretty much it. Thank you for attending, and I look forward to seeing you at the next presentation coming up next month. I believe it's going to be on August 16th, and it's building Rust web applications, and we're going to use HTMX as our client-side library. So with Leptos, we did Rust on the client and server. With HTMX and Actix Web, we're going to do HTMX, which is very little, if no JavaScript, but you get the same client-side benefits, and then Rust on the server for building the web application. All right, that's it. Thank you all so much. Take care.